All right, this intermediate level session is called Chemical Weathering of Soils and Parent Materials. And we have two types of weathering that we're going to talk about. We won't be addressing physical weathering today. That's really another word for that is disintegration. But we will be talking about number two, which is chemical weathering, and that's decomposition. And you can see pictures of both physical weathering and chemical weathering. The picture on the lower right is of calcium carbonate or limestone. And so you can see how it dissolves. This is a very close-up photograph, very, very close-up. And you can see how it dissolves through the process that we'll be discussing later called carbonation. Well, let's talk about weathering in humid soils since that's what we're dealing with here in Virginia. So if we have an environment that's wet enough for chemical weathering to occur, and the reason I say wet enough is because moisture is an absolute necessity for chemical weathering. We will not have chemical weathering in the absence of moisture. One other factor that we need to have to promote chemical weathering is we have to leach the byproducts from the soil system. And if we do both of those, we have moisture and we leach the weathered byproducts, flush them out of the system with the water, then chemical weathering does two major things. It decreases the particle size, and I just drew an arrow to let you know how decreasing particle size is absolutely the same as increasing the surface area. All right. We also decrease the cementation, so you can imagine bedrock that's strongly cemented becomes weathered and it becomes less cemented or eventually not cemented at all. We also have decrease in the stability of the primary minerals. So primary minerals form deep in the earth, when the bonds are broken by chemical actions, then they begin to become unstable, and that's when they break apart. We also decrease the cation exchange capacity and the base saturation. So basically the ability of the soil to hold nutrients and then the amount of nutrients that are being held. Both decrease, as does the pH over time. Well, what else do we increase when we weather a soil or a parent material? Well, we increase the porosity. And of course, if we increase the porosity, we decrease the bulk density. We also increase the amount of clay and other secondary minerals. And clay is the number one secondary mineral formed in soil. Clay and other oxides like iron oxides or aluminum oxides. And so we have an expression that we use, and we say that soils are clay factories. They make clays, and that's true. And then the soil depth increases as chemical weathering proceeds. So let's learn a little bit more about these now. One of the primary concepts in weathering is that weathering is dynamic in soil. And the reason is because the equilibrium is seldom maintained. So weathering takes place until it reaches what we call a dynamic equilibrium with the conditions and the forces in the soil. All the processes, all the conditions of chemistry and temperature and everything are in equilibrium, and then weathering would stop. But as soon as one condition changes, just such as having erosion or burying the soil or having a change in climate like we're experiencing, weathering is altered and rejuvenated because it's out of equilibrium. And so this graphic in the lower right-hand side kind of shows that equilibrium. And again, it is a dynamic equilibrium in soils because it's almost impossible to hold all the conditions that influence weathering and hold them steady for a very long period of time. They're in constant flux, one or the other. All right, where does the chemical weathering take place in the soil? Well, most of it does take place near the soil surface. And the reason is because there are more things that act to enhance weathering. So this is where we get air exchange nearest the surface. We do get air exchange deeper, but not much. We have very dynamic temperature changes. If you ever want to try something interesting, take a thermometer and put it about 1 inch above the soil surface, and then hold it at eye height. And you notice the difference in temperature at the soil surface. It's very interesting. Don't lay it down, though, or it'll explode. We get frequent wetting and leaching because oftentimes we get low rainfall, and it might not wet the soil very deeply, but it will wet the surface. Of course, plant growth. Look at the root system on this excavated cedar tree on the right, and you can see that most of the root activity is taking place in the upper 30 centimeters of the soil. And of course, the organic acids are released both from the roots and from the leaves that decompose on the surface. That happens at the surface. And microbiological activity is most intense in the upper part of the soil too. That also affects chemical weathering. But we get frequent and intense cycles of wetting and drying, freezing and thawing, shrinking and swelling, and then other things that do affect the weathering of the soil. So which soils weather the most easily? Well, just in general, it's soils that receive water that percolate through them at a moderate rate, and they leach out the weathered byproducts. So if you have a soil that has a slowly permeable subsoil, it's not going to weather very rapidly because the weathering releases byproducts and they saturate the water, and then that slows down the reaction rate. We need to flush the byproducts out of the system if we're going to continue the process. All right. Soils with fluctuating water tables are ones that weather quite rapidly, and so that's because they get wetting and drying cycles in the subsoil as well as in the topsoil. And then soils with easily weathered parent materials, and just to define those real simply, those are the ones that are low in quartz and high in unstable primary minerals. If the primary minerals are stable at the Earth's surface, they're not going to be very easily weathered. And for an example, quartz. That's why we single out quartz, you know. We're picking on quartz in this case because it is a very stable primary mineral, and therefore even at the Earth's surface, it does not weather very rapidly. So which parent materials weather most easily? And just simply, it's the parent materials made of primary minerals that are unstable at the Earth's surface. So just very similar to soils, it's the primary minerals that are unstable. And then primary minerals that are low in secondary minerals, such as oxides and quartz, because secondary minerals that form at the Earth's surface and quartz are both very, very stable. All right, so you can look at the graphics here and you can see some examples of how water enters the rock system, the ecosystem. And you can see how it might affect weathering deep underground. And this is an interesting graphic because we don't often think of deep activity going on, but what happens a lot of times is that bedrock is actually chemically weathered long before it comes close to the soil surface through erosion. And that is what lets soil form more easily. If the bedrock was not, pre-weathered, then it would take much, much longer to go from bedrock into soil. But luckily, that process starts up to 10 meters down in the ground, and then that prepares that bedrock for weathering into soil at the surface. It completes the process. All right, so we have 5 types of chemical weathering. Now, I'm not going to throw a lot of chemical formulas at you, but there's 1 or 2 that examples that I think will help. And what I've got is I have a slide for each one of these 5. We'll cover a couple of them, and then we'll take a little break for questions, and then we'll resume. So hydrolysis, and that's when hydrogen substitutes for another positive element. So hydrogen has a charge of +1. So when it substitutes for another charge, another element that has a charge of +1 inside of a mineral, then that mineral becomes unstable or unstable. All right, that's called hydrolysis, and that is the major chemical weathering process. All right, secondly, we have carbonation, and that's dissolution, basically things that dissolve. But in this case, we're dissolving carbonate. And what types of rocks are formed from carbonates? Well, mainly that's limestone and dolomite. And of course, if you live in the Ridge and Valley, you're extremely familiar with those 2 types of rocks because they're so common in this part of the world. Then if we go over the mountains into Tennessee and West Virginia, we find the same thing. Kentucky as well. All right, and in the next one that's most common is either extraction or uptake. Now this is where either fungi, bacteria, and archaea are a type of microorganism that once were thought to be bacteria, but now they found that they are actually distinct type. They can extract elements directly from the rock as an energy source. And when they do, that causes an instability in the crystals that make up the rock. And so the rock becomes unstable and starts to break apart. And plants uptake nutrients from humus and clay, and it causes those to become unstable. It actually can uptake nutrients from within the humus and the clay as well, if it's a strong enough pull. Then we have oxidation and reduction, and that's either the gain or the loss of electrons. And the biggest difference we'll discuss later is the solubility that results, because oxidized elements are crystal and solid. They're insoluble. But if you reduce that element, then they become insoluble elements. I'm sorry, they become soluble, and they can move in the groundwater. Okay, and then we have hydration. And hydration, the difference, think of hydrolysis is hydrogen. The first 5 letters, hydro, refers to hydrogen, not to hydrology. But on hydration, that HYDR stands for water. And so that's when minerals take water into their crystal structure, and that changes the volume of the structure, and that leads to instability as well. Okay, we'll look at 2 of these, and then we'll take a break. In the upper graphic, upper left-hand side, you can see that if you have an organic compound such as humus, and you add hydrogen, in the form of, this is actually water, H2O. So you expose that element to water, and if you'll note, and I hope you can see my cursor here, that one of these hydrogens replaces the compound or the element called R2. And so we get the oxygen that was shown in blue on the left-hand side, shown in red over here, now has a hydrogen attached to it instead of R2. The R2 replaces the hydrogen in the original water molecule, and so you have a disruption of the crystal and a replacement, and this leads to instability. Okay, another example just below that, we have a hydrogen to hydrogen bond, and if we expose that to more hydrogen and chlorine, then eventually we get hydrogen replacing one of the chlorines. So we take the hydrogen from here, a bond breaks and releases this hydrogen. It comes over here and replaces this chlorine and kicks it out. And it combines with the materials that are in solution shown up here. And so then we end up with a less stable mineral because the bond is different. And third, we have an example where this is actually a feldspar formula. I don't expect you to remember this formula, but let's just look at this real quickly. We essentially have potassium here, which is a positively charged ion. And if we expose it to water, and again, this is, H2O, two of these hydrogens, so this would be 2 molecules of water. Well, these 2 hydrogens replace these 2 potassium ions, and then you form a new mineral. And then those 2 potassium ions take the place of the hydrogen and combine with the hydroxyl and forms a different ion that's in solution, and that's hydrolysis. Okay, so let's stop now, and if you'd like to, you can turn on your chat button, and then if anybody has a question about anything that we've covered so far, I'd be happy to answer it, or at least try to answer it for everybody's benefit. And again, this is being recorded, so this would be a good time to take a look at it. I'm going to be trying to link up to a survey tool that we have at the same time and give you access to that. If nobody has a question, this is a good time to take a stretch break. We certainly have found out that that taking a physical break is an important process in learning. In fact, we found out that learning is actually easier if you're moving. So I know that you've seen examples of times when people are walking around a room reading a book, and you think, well, how in the world can they do that? They must be so distracted they're not learning anything. But actually, they're probably learning better than somebody who's sitting down reading. Well, this survey that I posted to you is a place where you can let me know if you have training needs. And I believe there's places where you can contact me directly and say, none of the things you mentioned on the survey fit my needs, but something else is important to me. So just be sure and contact me. And if it's soils related, I'll either try to address it or I'll refer you to somebody who can. Well, I don't see that we've had any chat questions, so I'm going to go ahead and go back and get going with the rest of the PowerPoint. Okay, so we have carbonation, and again, we're calling that the dissolution or the dissolving of carbonate out of rock. Well, of course, we have limestone, and we know that we have cracks in the limestone near the surface, and those cracks, when they come to the surface, the soil material and the dissolved limestone actually comes down, enters these cave systems, and travels eventually to the groundwater system. Okay, so in fact, this large valley may have been a sinkhole at one time itself. So think of these as sinkholes and this dissolving of carbonate. And it happens when you add carbon dioxide to water. But that dissolution is taking place underneath the soil because that's where the carbon dioxide and the water combine. They don't combine up here in the air. They combine in the soil. And that's why if I had a piece of limestone and I put it on top of the soil, it is not going to weather as fast as if I cover it with soil. So this is what limestone looks like underground. This is what it looks like when it's exhumed, or basically when all the soil erodes away. And now you can see this pattern of dissolution in the limestone rock. I think it's a fascinating picture. Okay, now we have uptake and extraction, or extraction. And essentially here is where we have minerals that are being taken up by the plant. And so if we have a clay particle right here in the soil, well, right here, or if we have humus, organic matter that has minerals attached to it, the plant will do an exchange reaction and take up those minerals up into the leaves. That's a pretty simple process to understand. And then if we have that, if we harvest that plant material and then remove the material, and of course these horses are mobile, so they might take that material over into this pasture before they redeposit it, you might say. And over here we can see harvesting of grain crops, but that material is leaving the system. So we're losing material. So what's happening is that as the plant takes up the elements, they're lost from the clays, lost from the humus, and then that causes instability in those minerals. And then if they're lost from the system by exporting, then we have instability, and it actually increases weathering. Now here on this rock you can see a slightly different process, and this is where we have lichens that have grown into the crevices of rock, and those are actually extracting the fungi, and the bacteria in here are actually extracting elements directly from the rock. And the interesting thing about this picture is you can see where these lichens are positioned along the cracks here, and you can tell that they probably started in the center and just grew out and out and out until they got larger and larger. But look what they did to the rock when they left it behind. This is a more highly weathered rock than this material, and that's indicated by the light color. So I really like that picture. I think it's very instructive. All right, now we have oxidation and reduction. So again, essentially, if you lose an electron, in other words, one of these electrons comes from here, from this atom, and comes over here to this atom, then that is called oxidation. So this one loses the electron, but this one gains it. So this element is said to be oxidized. Now in this case, this element gains an electron, and when it does, it becomes more negative, and then that ends up, it's said to be reduced. So losing an electron causes the charge to go up. Gaining an electron causes the charge to go down, and that changes the solubility. If both of these are solids and this one becomes oxidized, it will again be solid. It will be a crystal. If this one's a solid and it becomes reduced, it will become soluble, and then it can be leached, and the leaching is what causes the weathering. Now here we have hydration, and essentially where we've added water, you can see the background crystals and rock here, and this new mineral has absorbed water, and that has destabilized the structure of the original rock. And so a new mineral is forming, and of course it has a larger volume because it absorbs water. You can see water coming down in here and changes the volume, and so that causes instability and weathering. And this rock is meant to be one that is high in gypsum, and I should say calcium and sulfate. And then when water comes in and is added to that, then you form gypsum, and then that expands in volume, and you can see it actually precipitating around the cracks where the water comes out of the rock. All right, so let's talk about the fate of the byproducts and all. So many of the soluble elements, so the byproducts are soluble. So if we can move them out of the system, then we increase the weathering. If they stay in the system, then we reach an equilibrium and weathering slows down. So they can either be temporarily adsorbed onto charged surfaces. So, you know, there's an exchange between what's on the root and what's on a humus particle or clay particle, and that exchange takes place. We've already discussed that. They can be taken up by the plants then and recycled to the litter layer. So they come up into the tree, the leaves fall on the ground, the leaves decompose into humus, then they're taken back up into the tree, and then the cycle renews itself. They can be lost from the system by plant removal, and we showed you that earlier, or they can be lost from the system through leaching to the groundwater. And of course, that's a concern if the elements are nitrogen or phosphorus because of the pollution potential. That's also arsenic and copper and other elements as well. Well, here's an example of losing elements. So if the material that we're worried about is insoluble, in other words, instead of being reduced and soluble, let's pretend that it's a mineral, but it's in the groundwater. And if it is, I'm sorry, not in the groundwater, let's say that it's attached to soil particles. How can we increase weathering of particles that are attached to soil particles? Well, we can erode those soil particles and the attached elements from the system. That's how we lose them. So they can either be temporarily adsorbed onto charged surfaces, and here you see this little cartoon where you have a mixture of materials that are moving in solution. Pretend this is soil solution moving between two clay particles, and they're all positively charged on the edges, which is not realistic. But let's say that these materials are moving through, and the two negatively charged ions latch on to the edge of the clays, but the positively charged materials move on through and out of the system. All right, now we have a clay or an organic compound with those extra elements on it. Well, what if those materials are here in the field? We get a rainstorm, and you can see gullies all the way up onto the hillside, and those materials are eroded from the field. Then we've lost them from the system. All right, what controls weathering? Well, one thing is soil depth. So, you have deep weathering of bedrock, and when the weathering becomes extremely deep, it slows the processes. Earlier in the slideshow, we showed a list of processes that kind of promote chemical weathering. And you remember how we emphasized that they took place pretty much in the most intensely in the upper 30 centimeters of the soil. We had a picture of a cedar tree with its tree roots exposed and painted so you could see them. Well, imagine then that at 10 meters down or 5 meters down in the soil, there aren't very many roots, and the bedrock or the soil is very highly insulated against those processes. Well, if that's the case, then weathering is going to slow down in those deeper cuts. And here you can see some deep bedrock in the ridge and valley. And then on the right, we can also see some deep, deep soil weathering. Well, the intense chemical weathering processes are going to take place right up here, and there are not going to be very many processes taking place down here where you reach bedrock. Okay. So controls on weathering besides soil depth or climate. So chemical weathering increases if both moisture and temperature are high. And here is a picture of a moist, warm area in the tropics, and you can see just how deeply you have to go before you reach what's called saprolite, which is completely weathered bedrock. And then actually you have to get all the way down here to this ledge before you reach material that is still cemented together. So this would be your first bedrock layer here. This would be saprolite, and these would be the substratum, and then this would be the lower parts of the soil. And you can see for scale, look at this gentleman here. And then chemical weathering decreases as moisture decreases regardless of the temperature. So if you have soils that are forming in the desert, and they do form in the desert, just not as very rapidly, there are just very few chemical processes taking place in this soil. There are some, but not many compared to this soil, because this one is dry and moisture deficient, and this one is not deficient in moisture or temperature. And of course that explains this graphic, and that's why in the tropic regions where you have high temperature and high moisture, we get deeply weathered soils. And then we also get higher weathering in slightly northern climates, not extremely cold, but slightly northern climates, and that's because the precipitation goes up and the evapotranspiration is less. So here we have sufficient moisture in the temperate zone, but we don't have we have the temperature, but we also have high evaporation compared to moisture. So here you can see how the moisture exceeds the evaporation. We get deep weathering. Here, where moisture exceeds evaporation, we get weathering, shallow weathering. But here where evaporation exceeds moisture, we don't get much weathering. All right, also, if we have a persistent high water table, we're really going to restrict weathering because everything goes into solution and the water stays close to the surface. And the problem is that you get saturation. That water is saturated with elements, and so diffusion does not take place between the soil and the water. And so weathering slows down. All right, another thing to think about is that effectiveness of precipitation. We had an example just a minute ago where we talked about the difference, the comparison between the amount of precipitation and the amount of evapotranspiration. And so what landforms would we have highly effective precipitation? And that typically would be either the level landforms, which would be summits, tend to be level, and terraces tend to be level. But then we also get excess moisture on foot slopes because we get runoff from the side slopes. So all of those have increased effectiveness of precipitation. It's the shoulders and the back slopes that have decreased evapotranspiration because they suffer runoff. Also, we can look at aspect. If we have a southwest aspect, then we have lower effective precipitation. It dries out quicker. If we have a northeast aspect, it has higher evapotranspiration. It does not dry out as quickly. So to summarize, in Virginia, we have a temperate climate, and that provides enough warmth and enough moisture for chemical weathering in our soils. We have a humid, temperate climate. And in our oldest soils, many of the byproducts of weathering have been completely leached out unless there's a water table or extreme runoff or a water restricting layer that has prevented that. And that's why many of our older soils are bright red, highly weathered, and not very fertile. Okay, I'm going to open up the chat again and see if anybody has questions about anything that was mentioned today. I hope that you enjoyed today's talk. Again, we find that chemistry and weathering tends to be the least interesting part to people, but I tried to provide enough graphics that you could relate that to something that you've seen. And by tying it to landscape positions and rock types, then hopefully it starts to make sense based on what you see when you travel around the state. All right, well, if there are no questions, then I'd like to invite everybody to click on the survey link that I provided in the chat link, and you may add your input as to what types of training you would like to have in the future. And if not, we will do an intermediate training again next month. And I hope to have you back again. I hope everybody has a great day and enjoy the rest of your lunchtime.